So now we want to give you some concrete examples of computations of tensor products. I warned you from the off that when Holger gave this construction of the tensor product, that it's sometimes not very useful to operate with that construction. Because it's similar as in singular homology, this construction is a quotient of a huge module, and sometimes it's very complicated to prove properties using that. Nevertheless, it's important to know how to write elements in the tensor product. And remember from Holger's video that we had this map from the product of two R modules. So M would be a right R module, N would be a left R module. And then we had this map that had the tensor symbol to the tensor product. Now, the image of an element M, N, you denote by this small tensor, Mn. And the construction of this tensor product was such that it was generated by those elements, meaning that any element here in the tensor product is a finite combination, it's a finite sum of these elements. And these elements have a name. Such an element in the tensor product is called an elementary tensor.
Yeah. That it is generated is easily seen because this M tensor N was a quotient of the free abelian group on the set M times N. It's already sort of surjective to this free abelian group, and that then, of course, descends to a surjective map if one composes with a canonical projection.
So let me just write this important sentence. The elementary tensors generate M tensor N as an abelian group.
Yeah, I mean, actually, it was not a surjective map to the free abelian group, but it's the inclusion of the basis. This is how I should have put it, and therefore it generates the whole group.
Right. Yeah. And sometimes what one does in practice is when defining maps out of the tensor product, one just says what happens to the elementary tensors. But of course, you have to, there's an implicit check that you have to do in your head when you define a map out of the tensor product by just saying what are the images of the elementary tensors, because you have to argue that this map is well defined, because this was actually a quotient of the free abelian group of these elementary tensors divided by some complicated relations. So basically, what you have to show when you define a map out of the tensor product using the elementary tensors is, well, you have to show certain relations. You have to basically show that the map from M tensor N to this and going further satisfies the bilinear relations.
Yeah, you have to. Yeah, you just have to check that the three relators that generated the subgroup U, that your map will vanish on those relators. This is what you have to show. Yeah,
exactly. So, for example, if you have M times R tensor N, this should be mapped to the same element than M tensor R times N for an element R in the ring.
Right.
And similar for if you have a sum M1 plus M2 in brackets tensor N.
And using this technique, we can now formulate and actually write down the corresponding isomorphisms of some elementary properties of how to compute tensor products. And one of these is a sort of distributivity property, namely if you've got a right R module M and you form the tensor product over R with a direct sum of arbitrarily many left R modules N, so like this, then it turns out that this is actually isomorphic to the direct sum over the same index set of those tensor products M tensor R N. And now, like we just said, it's enough to describe this isomorphism on the elementary tensors.
Just add this I here.
That's right. They don't have to be the same. Thank you. I mean, it can be anyone's. And then I can write down the isomorphism on elementary tensors as follows. So every one is of this sort, M tensor, and then some element in the direct sum. I can describe this as some sum in a unique way of elements Ni. And guess what? I will map this to the following linear combination of elementary tensors, just some I in I, M tensor Ni. And this is an example of an isomorphism defined, well defined in this manner. Yeah.
And it's implicitly understood that this sum is a finite sum. So there are only finitely many ni's that are non-zero in this notation.
That's why it's direct sum. Okay, and of course, if we have that property, the same property also works on the other side. So let me just write it down quickly without writing down actually the isomorphism. Ni tensor R M is isomorphic to direct sum I Ni tensor R M, and now we have swapped the notions of left and right. Yeah, now M is a left R module and Ni are right. Yes, right R modules. Okay. Third important property for calculating tensor products is actually if you just consider the free module of rank 1 and form the tensor product with that one, so M tensor R with the R module, with the left R module R, then actually nothing happens. This is isomorphic to M. And again, we can say what the isomorphism is. An element M tensor on an elementary tensor is just the multiplication. So this is the isomorphism, M times R.
Let me just...
Yep.
Sorry to bother you.
Ah, sorry, yes, no, this is... yeah, right, yeah. No, that was an important remark, yeah. Okay, so it's just the multiplication, yeah. So,
yeah. Okay, so let me just emphasize again. Giving these maps in terms of the elementary tensors is an implicit small exercise for you to check that this map is really well defined on the tensor product.
And maybe, yeah, just for completeness, of course, we have it the other way around also. So R tensor R M is isomorphic to M, and the map is R tensor M goes to R times M. And finally, we can also combine now these properties. So for example, if we have M tensor R with some free R module of rank n, then first of all, we can consider R to the n as the direct sum of n copies of R and use the distributivity in property 1 probably, yes. And therefore, this is isomorphic to M tensor R to the n. But now we use property 3 and see that this is actually isomorphic to M to the n. So whenever you form the tensor product over R with a free R module of rank n, you just get n copies of the module which is on the other side of the tensor product.
And to check that these are really isomorphisms, it's very useful to look at the inverse map. So for example, here, from M to the tensor product, the inverse map would just take M to 1, so the unit in the ring, tensor M. And then you can easily check that this is an isomorphism. Because usually maps out of a tensor product to check that they are injective is usually hard. So it's very convenient to have really the inverse map. Because to check that both composites are in the identity is much easier.
Okay, so I'd suggest we look now at a little more inspiring example and see if we can now apply all these things we know about tensor products to commute them. So how about we take the cyclic module, Z module of order n, and form the tensor product over Z with Z mod M Z. So what would that be? And
I suggest that, okay, there is an answer here
yeah.
that we can give, but it's maybe good to look at the smallest non-trivial example, which would be, well, you could also take Z mod 2, but let's first look at this example. So I claim that this is 0. This is just a 0 module. What do you do? How do you show that? Well, one way to show that is to show that every elementary tensor that you can write down is 0. And since this is generated by the elementary tensors, this has to be the 0 module. But if you have an elementary tensor, so A tensor B, then it happens that you can write this as A tensor 2 times B prime. And why is that? Well, because 2 as an element in Z mod 3 is invertible. So 2 as an element in the ring Z mod 3 is invertible.
Yeah, that's a bit problematic, right? Because this is just a Z module right now, so invertible is...
That's true, but we're using the extra structure that's hidden, that this is also a Z mod 3.
So it's good that you wrote it in this way and did not write it's 2 times 1/2 B. This would have been,
Okay.
Yeah.
In any case, I can write an element in Z mod 3. I can always write it as 2 times another element. But now I use the fact that these are elements of this tensor product over C. Therefore, if I have a 2 here, I can bring it to the other side. But 2 times something in Z mod 2 is always 0.
So this was using the R balance property of the inclusion map, the canonical map of the tensor product.
Exactly. And so we have shown this. All right. What is the answer here? Well, the answer in general is that this is Z mod the greatest common divisor, GZD, of n and m. And in that case, it was just 1, so we have Z mod Z, which is just a 0 module. Maybe let's call this a proposition, or I don't know, a computation. Yeah, let's check this.
Yeah, so maybe the properties we've seen so far beforehand here are not very useful for seeing this, but we know a little more about the tensor product. Namely, in 2 videos ago, we showed that it's actually a right exact functor. And this can help now, so let's put this as a proof of the proposition. Namely, we can consider the following short exact sequence. So what do we have here? Z mod nz. So we sort of use the defining short exact sequence of Z mod nz. Namely, it's the co-kernel of this multiplication by n map. Right? This is a short exact sequence, and now we apply to this the tensor product functor over Z with Z mod mz. And since it's right exact, then the portion here on the right will still be exact. So out of this, we get that Z, which one do I want to take? Tensor from the right, right? Yeah. So Z tensor Z mod mz. Still the map multiplication by n. Z tensor Z mod mz. And then we see that here on the right-hand side, we arrive at the module that we are interested in, namely Z tensor nz, Z mod nz tensor Z mod mz.
It's really important to distinguish the n and the m's.
Yeah, okay. That's right. Right. Yes, I feel guilty here. Yes. M. I think this m is okay.
This is okay.
Okay. Right, and this is exact. And now, as we already saw in the last video, exactness of this 4-term series says precisely that this object here is the co-kernel of this homomorphism here.
Yeah, we can simplify this co-kernel because this was isomorphic to, so if we have R tensor over R, we can somehow skip the R in the isomorphism here.
Property 3 or 4.
Yeah, the same here. And under this isomorphism from the properties, which is even multiplication if you want, then this is still multiplication with n. So we have to compute something very concrete now, the co-kernel of the multiplication with n on this finite module Z mod nz.
Yeah, and the assertion of the proposition, of course, already tells you what the answer is. So what we in fact have to show is that instead of this guy here, if we introduce the module Z mod GCD and MZ, then this should again be an exact sequence. So this is sort of the task we are left with. We need to show that the following sequence here is exact.
which is good. Now all the tensor products are gone. This is just a module, an elementary question about C modules. And you see how this goes. You should, in most cases, maybe not in every case, like the example above, I argued with the elementary tensors, but in most cases, it's actually useful to avoid dealing with the individual elements. And here we just use right exactness to transport the question to a question about C modules. So now we have to show that. I think what's well, first of all, this map here is of course meant in a way that this is induced by the projection from Z to this quotient.
Yeah, so the greatest common divisor is in particular a divisor of M. So we do have this projection, and this is then automatically surjective. So exactness here is no problem.
What's really to show is, what we really have to show is that the kernel of this map is the image of this map. What's also clear is that if we start from here, multiplication with n, and then we go over there, because n is divided by the GZD, that this is 0.
Yeah.
So the image is in the kernel. The only thing that's really left to show is the kernel also contained in the image? And this is computation one should do with using elements.
So let's do it. Let's take an element here with the property that it maps to 0 here. So what do we know about this element now? Being 0 in that quotient means it is a multiple of the greatest common divisor of NM. Maybe to not always write it, let's call it D, right? So this means that X is equal to D times something, say A. And is that right? I mean,
sorry, what are you?
Yeah, I'm thinking.
Now I think this is completely correct. Of course, if X is mapped to 0, then X is D times A, and then since D is the greatest common divisor, we have a representation. I mean,
you're just saying this is now an equality of integers. This is how it's.
This is
so,
an
yes,
equality
this is
of integers.
What? Yeah, right. So this is an equivalence class, but now X can be represented as a multiple of D. This is what I had meant here.
Exactly. Yes. So let's for some A
in Z.
In Z. And now use that the GZD can be expressed as a linear combination of n and m. So it's, how do I write that? I write it as n times n prime plus m times m prime.
That's the so-called Bisous identity.
Right, it had a name. And now let's just see how this tells us, hopefully, that X is coming from multiplication with n. All right, so yeah, right. So we have this, and this implies that this X as an element in Z mod M is n times n prime A. And therefore in the image, because this m times m prime A can be ignored because the multiple of m is just 0 in this group, and therefore it's
in this quotient that's represented by n times n prime times A, because this one is a multiple of m. And yeah, so the kernel, an element of the kernel lies in the image, and that's all she wrote. Okay, so
note, by the way, if n and m are not co-prime, then this is not injective. Did I say this correctly?
It's well, if they are not co-prime, then it means there exists a non-trivial co-kernel, which means it's not surjective.
And since they have the same number of elements, then it's also not injective. Yes.
Okay, right.
Yeah, actually, you can show that the kernel of that map is also isomorphic to this by a similar argument. Okay, so what do we have now? All these examples were about C modules. Let's go back to this fact, to this general proposition that we proved now. We can compute what happens with torsion modules, finally generated torsion modules. We also know what happens if we have here just C or copy of C's, because that's just the rule that tensoring with C doesn't change anything, and if you have C to the n, it just gives you so you can draw out the sums. So basically we can compute tensor products of two arbitrary finitely generated C modules, because every finitely generated C modules is of the form bunch of C's, direct sum with modules of this form.
And yeah, finitely generated Z modules is exactly the same thing as finitely generated abelian groups. So really we can compute tensor products of abelian groups now.
Finitely generated abelian groups.
Finitely generated abelian groups, yes.
Shall we look at a non-finitely?
Yeah, maybe the nicest or coolest infinitely generated Z module or infinitely generated abelian group is Q. Q as the Z module. So maybe one can ponder what's this tensor product.
Right. And I think it doesn't lead very far to look at individual elements and to argue with the construction of the tensor product. Well, first note that, as a side remark, this is a statement. I mean, so far there is no statement, but when we computed this, it will be a statement about Q as a C module. If you regard Q as a Q module, then of course tensoring over Q is just Q. Because again, tensoring over Q with Q gives you back whatever is here, so this is just Q.
Always keep in mind the category. It's Q as a Q module.
Yeah.
As a Q vector space.
So what about if we tensor over C? Is it still the same? Well, at least we still have a map here to Q, and the map is just taking two rational numbers and taking the product of them. It's still well defined. So if you have A times n, tensor B is sent to the same element as A tensor n times B for an integer n.
And it's also linear in both A and B.
Linear in both variables, right? So the map, makes perfect sense. Surely I hit every element here, so it's a surjective map, that's also easy. Question is this an isomorphism?
First question is it maybe split surjective?
That's right. So can we find a map back like that? And indeed we can, because that's very similar to the split or the inverse that we had in this case. So the map back is given by, so let's call this M, and let's not write it dash as a dash arrow. There is a map S, and S maps Q to Q tensor 1. So that's also certainly a well-defined map. And again, we regard everything as C modules. So these are, for our purposes, these are all maps of C modules now.
And the composition, indeed, S and back M is the identity. You know, Q tensor 1 goes to Q times 1. So it is a splitting, and that means it's split surjective.
So it's obvious. Which way? First S and then M, right?
Yes.
And first means writing functions means exactly the opposite. Anyway. So what does it mean? It means that S is injective.
Well, we now have to consider the other composition and see if it's also the identity on the tensor product.
Right. Either we consider the other composition, or we look at. Well, no. Let's look at the other composition.
Probably the easiest thing to do, right? If I take S after M of an elementary tensor again, So let's take A tensor B. Then this is S of A times B, and this is A times B tensor 1. But now again we have this R balanced property, and that tells us I can move over this B.
But B is not an integer.
Thank you. I almost made a mistake here. I did make a mistake here, so let's see. These are rational numbers, so I have to make it an integer first. Yeah.
Exactly.
So how do I do this? I multiply with the denominator, right?
Yeah, maybe it's good from the start to write these numbers as fractions of integers. Maybe that's better. Maybe it's enough to do it with one of the numbers. I'm not sure. Yeah, let's write it. Let's just replace this by this was b, and now instead of b I write c mod d, and maybe let's call this q. Okay, so what we have here is q is a rational number, and c and d are integers. I mean, d should not be 0, of course. And then we can keep all that, but then maybe it's easier to argue.
Mm-hmm.
So you wanted to pull over something.
So I guess I write this one better as d over d. Maybe this makes sense, right?
Yes.
So here I've got tensor 1, but this is an element in Q, so here I'm allowed to write d over d. Right? And now I can do what I wanted to do before. Integers, I'm allowed to move them over. So this is the same thing as... And now here I've got an integer c here, and I can again move it over by the R-balance property. So this is Q tensor c over d. So we see that starting with some elementary tensor and going ms, we arrive at the same elementary tensor, and that means not only on elementary tensors but on the whole tensor product. This composition is the identity, and actually now we've shown that both compositions are the respective identities, so it was an isomorphism. So the result is that Q tensor Z Q is isomorphic to Q.
Mm-hmm. But it's a kind of coincidence. So this comes from a general rule. This just happens to be the case after this computation.
And it's a different result. It's Q as a Z module, right? Here it was Q as a Q module. Yeah.
What about R?
Yeah, that's good in the logic. We had finitely generated. Now we have countably generated. Now let's do uncountably generated.
So that's something unusual. We look at R as a C module. Okay.
Mm-hmm.
Is it still, I mean, the first naive guess from the previous one would be that this is just R.
Mm-hmm.
But let's see. All right, so what do we know about R as a C module?
Well, first of all, I would say R is a Q vector space, and as such, there exists a basis. So R is definitely a uncountably dimensional vector space over Q, because there are uncountably many transcendental elements.
Exactly. So we have an isomorphism with an uncountable index set, uncountably many copies of Q. And this is a Q vector space isomorphism. But in particular, if it's a Q vector space isomorphism, it's also an isomorphism of C modules. Mm-hmm. Okay? So in particular,
it's an isomorphism of abelian groups. This is just saying.
Yeah.
Yes.
And since we already have proven something about Q, let's just put this in now, so we know this is a sum of Q's. Okay, maybe a bracket to make it clearer. All right, so now we can use the fact that the tensor products is compatible with direct sums and even uncountable sums.
So we get a double direct sum, which we can pull out.
Sorry. What we then have is this. Well, it now, if you look at this double sum, I mean, I is an uncountable set. Now you have a sum over the index set I times I, if you want. Mm-hmm. It's still an uncountable set of the same cardinality as I.
Yeah, so algebraically, this is just...
So algebraically, this is just...
uncountable, or countability, or sort of cardinality of R many copies. of Q
Maybe
tensor ZQ.
Let me put it here.
Yes, and for the summons, we already found out what it is.
Let me say this is using a bijection of I tensor I and I. And this we just computed, so this is just Q as a C module by our previous computation. And we use this isomorphism here of R with this sum, so this is again R.
Yes.
So,
but R as Z module, that's important.
exactly, so let's just to see it all together. So R tensor over C with R is isomorphic to R as C modules. Okay, good to know. But if you look at this abelian group on the left, it also has the structure of an R module. Let me write it down on elementary tensors. So, is an R module this R? Sorry, should. Is an R module via this scalar multiplication. And therefore, we can ask whether this isomorphism of C modules also holds true as an isomorphism of R modules. Are these two R vector spaces isomorphic? Is this just the one-dimensional R vector space? And the answer is no. As R modules, they are not isomorphic. So, but
and of course, left R module is just a different way of saying R vector space. Yes.
Right. Okay, so how do we show that this is not isomorphic to R, or that it has a bigger dimension as an R module? One way to do that is to consider the following embedding of C2 into R as C modules.
Just by taking one rational and one irrational element, right?
Exactly. So let's map this to 1, and let's map the other basis vector to
square root
pi.
of 2 or pi, yeah.
Square. Okay, we don't do transcendental, yeah. Square root of 2. The square root of 2 is actually better. All right, so this is an embedding. And now we just tensor this map of C modules with R.
The problem being that in general, applying the tensor product is not left exact, so does not preserve injectivity.
In general not, but here indeed it does. So this is injective since R is flat over C. So this is something that we just use now as a black box to bring this to an end. I might come back to this in the next video. But it turns out that this is injective, and now by the properties in the beginning, this is just R2. Moreover, this map, this isomorphism, and this map, they're all compatible with this left R multiplication. So this is an embedding of R2 as an R vector space into this tensor product, and therefore, well, it cannot be one-dimensional.
Yeah, and actually, I mean, there are even uncountably many algebraically independent elements in R, so the 2 is just one choice. Yeah, we can take Z to the whatever there.
This is an infinite dimensional R vector space, but as a C module, as we have seen as a C modules, there are indeed isomorphic. So tensor product can consider many crazy examples. Tensor product has many funny properties, and there's a lot of fun to play around with that.